Good morning, everybody. This is Mrs. Hunsucker. I am your geometry teacher, and I thought I'd take a few minutes to go over the Unit 3 performance task. And I ask that everybody go ahead and print the performance task out in the Unit 3 module is where you can find it. And write down, as I move along, the important concepts, and you can probably get this performance task taken care of pretty quickly. For those of you that may have taken it and would like an opportunity to resubmit the assignment to improve your grade, I encourage that as well. All right, so we're going to go ahead and get started. It says that the segment CB is parallel to ED. So the arrows here indicate parallel lines. And segment CB is congruent to segment ED. Okay, and those are marked with these tick marks. It's asking you to prove the triangle's congruent using isometric rigid transformations. There are 3 isometric rigid transformations. One is a reflection, the second is a rotation, and the third is a translation. All right, so of the 3, they preserve size and shape. So can we reflect triangle CBF onto triangle EDF? Okay, if so, what is the line of reflection? Which side would be a line of reflection? So which side would you fold along? So that one figure that, so that one triangle flips onto the other. All right. Is there such a side in either triangle that you can use to fold along so that one triangle flips onto the other? So what I mean by that, without getting too detailed, is let's say we want to have triangle CBF flip onto EDF. Can we fold along segment CF so that the triangles flip onto each other or map onto each other? No, if you fold along segment CF, where is this triangle CBF going to end up? Okay, and it's going to end up somewhere over here and not here. Okay, so it's not, and if you try it with any other sides, it's not going to flip onto itself. Okay. It's not going to map onto triangle EDF. So with that said, I'm going to erase that as a line of reflection. So that this is a no. It's not going to be a reflection. Okay. The next choice is a rotation. Is there a point that remains fixed which you can turn triangle CBF so that it maps on to triangle EDF? Is there a point, a center of rotation? So when you think of the hands of the clock, where the hands of the clock meet at the center of the clock, that point doesn't move. Okay, that's a fixed center of rotation. What point can we turn triangle CBF onto EDF? So think about that. Okay, and hopefully you would say you can rotate triangle CBF onto EDF so that corresponding sides and angles map onto each other through a rotation about center F. Okay, so So the rigid transformation, that maps one triangle onto each other, onto is a rotation about point F. All right. But that's not all you have to do. It's really important that we read the question, what's being asked. It says, if we read it closely, outline the necessary transformations, and we did that. Using a paragraph proof, be sure to name specific sides or angles used in the transformation in any congruency statements. So how do we prove triangles congruent, right? So we prove triangles congruent by the following ways. If you recall, side, 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 angle, side, angle, side, angle, side, angle, angle, and hypotenuse leg. Now, when I say hypotenuse, you should say right triangle. We don't have right triangles, so we can rule that out, okay? So far, we have one pair of sides congruent, right? So how do we show that we have more than one pair of sides congruent? Well, there isn't really a way to do that, okay? However, so it's not going to be side, side, side because that's 3 pairs of corresponding sides. It's not going to be side, angle, side because that requires 2 pairs of corresponding sides, and we're not given more than one pair. If you notice in the given statement, it says CB is congruent to ED. That's all we know. All right, so it's either going to be angle, side, angle, or side, angle, angle. That we can definitely find 2 pairs of corresponding angles congruent. And the reason we can do that is, watch this, DE. Oh my, that's really bad. Let me see if I can move this. Nope, let me redo it. All right. All right, so DE and CB are parallel. Let's let DB be the transversal, okay? So when 2 parallel lines are cut by a transversal, remember the special angle pairs that are formed. And if you recall, there are same side interior, and those are the only ones that are supplementary. All right, there is alternate interior angles, and those are congruent. There are corresponding angles, and those are congruent. The only one special pairs that are supplementary are same side interior and same side exterior. And then same side interior, corresponding alternate interior. Yeah. All right. So those 3 pairs we're going to focus on. Which of the 3 pairs can we find congruent? Well, same side interior angles would have to be angles on the same side of the transversal DB. So here in here, those angles would be congruent, okay? This is the interior, inside the parallel lines. Remember I talked about the parallel lines, D, E, and CB being the hamburger top and bottom of the bun. Everything in here is your burger, your lettuce, your tomato, all that good stuff, your cheese. So this is the interior. So same side interior would be angles on the same, on the right side of the interior. okay, like these two here, or these two here, okay? But corresponding angles is, just a reminder, is these top 4 angles would slide onto these bottom 4. And we could say that this angle here would slide onto this angle here, right? But those are not angles inside the triangle, so that's not going to help us, all right? So it can't be corresponding angles either. All right, just saying. All right, so let's see if we can find what's left. There's alternate interior. So we know it's not same side interior. We know it's not corresponding angles. But alternating means back and forth. So what about this angle here and this angle here? They are alternate interior angles and they are congruent. So I'm going to say that angle EDF is congruent to CBF by the alternate interior angles theorem. So when you're making this paragraph proof, that's what you want to prove. Okay, you want to make sure you write that down, that include that in that paragraph. That's angle EDF is congruent to CBF by the alternate interior angles theorem. Okay. And we do have another pair of alternate interior angles, okay, when we let segment EC be the transversal, okay? So this time EC, and then our alternate interior angles would be here and here. So we can use 2 arcs to show those angles are congruent because they have the same number of arcs. So you would include that right here. So angle DEC is congruent to angle BCF. DEF, that should be DEF. All right, so DEF, you go from D that has 1 arc. The corresponding angle of D is B, that also has 1 arc. E has 2 arcs, C has 2 arcs, and then F. And they're all congruent for the same reason, by alternate interior angles. Now, if you look at this, why are the triangles congruent? Well, let's look. We have a pair of angles. We have 2 pairs of angles that are congruent. And we have a pair of sides. Let's not forget here and here. Now, is it going to be angle side angle where the side is the included side, or side angle angle? The included side, folks, is the side that both of the angles D and E share. So check that out. They share DE, and angle C and F share DC. So those sides are congruent. That's the included side. So you could say the triangles are congruent by angle, side, angle. Okay? Angle, side, angle. All right. So that would be your last statement to make. Let me start erasing some things. Okay, I can't. So then the last thing you would write is that the triangles are congruent. You would write this statement. This would be the last statement you'd make in your paragraph proof. And you would say they're congruent by side, angle, side. No, angle, side, angle, sorry. All right.